Hello everyone, I'm Krishna Kumar Chandran. Today I'm recording this video for an interview process with Escape. Today's date is October 12th, 2023. Um, in this presentation, I'm going to go through all my skills, experiences, and the projects that I worked on, which are mostly related to this position that I'm applying to. So my full name is Krishna Kumar Chandran, and I go by the name Krishna. So I am a software engineer with more than 7 years of experience. I did my Master of Engineering at University of Cincinnati, and I specialized in aerospace engineering, mainly autonomous vehicles, dynamics, and controls. And I'm also interested in AI. With respect to my work experience, I worked with Tata Consultancy Services in a team called Digitate. Um, and My recent job is was with Toad Drive. Um, Here I worked as a lead data engineer. I have also provided my LinkedIn and portfolio links. If you want to check my other projects which I didn't mention in this slide, please feel free to check those profiles. So in this presentation, I'm going to go through some of the important things. The main ones are mostly related to my past experience with Tor Drive, because that is so Tor Drive is an startup based out of Cincinnati, and they build autonomous vehicles for airport applications. Um, Now, in this today's presentation, I'm going to explain you like first introduce my team, like which is me and my intern. But Because some of the projects were shared projects, and what was our mission, scope of my projects, past projects, like some small projects which are relevant to this, and after that, I'm going to explain in detail about the data platform that I built. And I believe most of the skills that I used while building this data platform are directly relevant to this job profile. I also want to go through my deep learning projects, machine learning projects, and algorithms that I developed as part of my previous experiences. Yeah, let's get into that. So, as I mentioned, like I go by the name Krishna, and I worked as a lead data engineer with Tor Drive. I was the lead of the team, and I had an intern called Aaron. He is a software intern, and he mostly worked on the front end development. So, my team was the main mission of my team is as a data team, we are responsible for design, implementation, and continuous improvement of data pipeline. Um, we should produce product performance data to engineering, operations, production, and business teams quickly and accurately. And based on the data that we collect, it helps a company to make data driven decisions which are critical to its growth and success. So, as far as scope is concerned, first we were expected to design, implement, and improve all aspects of the data pipeline. So, as to give a small background, we as an autonomous vehicle company, there are multiple autonomous vehicles which also can be considered as an robots, autonomous robots. So these vehicles produce a huge amount of data in terms of sensor data, vehicle statuses. There are like multiple modules such as perception, planning, controls, mechatronics. These all runs in the system, and each and every module produces a very good amount of data, and these are crucial for us to understand if the vehicle or like the autonomous robot is performing as per the expectation. And as it is aim to be completely driverless, it is crucial for us to monitor all the performance metrics and make sure that all the possible scenarios are tested. So in order to do that, there is a as there is a huge data need. Um, our team's responsibility is to build that system. Not only that, we should also build all the tools to automate and facilitate data operations. It can be a web-based data platform or onboard GUI tools. It also can be some of the core ROS nodes like C++ code that we develop as part of the data collection. And also, we work with multiple teams to understand their data needs and to understand their data workflow. So that I work with all the team to incorporate their requirements. Next, I also worked on the CI/CD pipeline. So that like whenever there is a change made, it is pushed to GitHub and it is pushed to the repository, and then it's quickly integrated and deployed for the users. So I also worked on, based on this data that we collect, I also worked on the producing reports and dashboards, mainly the key performance indicators, which give the company very high level and detailed high level and accurate results on how good we are performing in terms of safety, reliability, and performance of the autonomous vehicle. I also work with the IT team to ensure the data security around data operations. Um, so finally, I also provide APIs for other applications. For example, fleet management system. A fleet management system is a central user interface used by the end users, and in order for them to monitor robots or like autonomous vehicles, what they are doing, what missions, and in order for the system to plan, to plan in a very high level, they need the data of some basic data of where the vehicle is and what operations they are doing, and those data are provided by the APIs that I develop, and it's based on all the data that we collect um, and we store. So, before getting into the main project, which is the data platform, I want to explain one small part about the key performance indicator, like why it is required and what all data is expected. So, key performance indicator is one of the report that we generate, which gives us weekly, monthly, and yearly, off yearly. It's a report that we generate um, on a regular basis, and it gives us idea of how well we are doing in terms of autonomous vehicles. The main ones are the safety, operation, and the reliability ones. um, like uh, what is the total number of missions that is done by the vehicles, and in which how much are how what is the total time spent in autonomous mode or the manual mode. And there are other data that we collect, for example, um, like average speed and average speed in autonomous mode, average speed in manual mode. So there are like multiple data that we collect as part of this key performance indicators, and these reports are produced directly to our end customers. The end customers use this data to make a decision on on planning their other activities, like how much autonomy is covered by the vehicles and how much autonomy how much manual work they have to do, and it helps them to process. To build a business process around this autonomous vehicles. So next, I want to jump into a data workflow. So before going to the data platform that I developed, I want to give a quick idea of what was used earlier and how our system, how the platform that I built made a change in their in that company. So all the engineering teams they use a ROS bag data for their development. And you might ask the question like why ROSBAG data is used for any robotics application and the system which is running on ROS, the robotic operating system. The data can be collected in form of ROSBAG, and ROS has multiple tools such as ROS Play or yeah, something similar to that, something of that sort to just play the data so that the topics are published from the ROSBAG, and they can be directly used by our algorithms and operate. So it helps. It is easier for our teams to uh, build or have an ROSBAG file as an input, and with that input they can test and develop their individual modules, being it as an perception module or planning module or control. Now, there is also a huge need of a ROSBAG data collection because most of our perception stack works based on deep learning, and deep learning requires a huge amount of data annotations. And here we are dealing with like five camera datas, two thermal cameras, and two lidars. So all these data are collected, and the process looks like this. So in a day, after the engineering team request operator team, they go to the field and they collect the data on a given conditions like daylight or rainy data or something like that. Once they collect the data, by end of the day, like it takes one day to collect, and by end of the day they store the file in a NAS storage. And once they store the NAS storage, it is available for others to download. It's usually like a shared location, and the teams who requested it, they go to the shared location, and they check for the data that they are looking for. And say in on a daily basis we don't um, on a daily basis we collect something like terabytes of data, and this is very huge. And so all the back files are like grouped together, or it there will be a multiple back file folders. So for each folder, every team, the workflow is first they will go to the share location, they will find the back file. Um there might be multiple like 20 to 25 folders. For each folder, what they have to do is first they have to download from the storage to their local computer. After downloading, they use a tool called Orvis, and Orvis works in a way like there should be two applications started at once. One is ROS code Orvis, and then play the ROS back that they just downloaded. um, Playing these videos, it usually takes 20 minutes, um, because like each back file has like 20 minutes of data or some it's not exactly 20 minutes, it depends. But usually like to play this data and to check what is going on, it you can consider like it takes 20 minutes. And for every try, like once they play, it starts from the starting of the time frame till end. They cannot jump back or they cannot fast forward, they just have to follow the Orbis. As there is no rewinding option or playback option, if they want to visit the data again, they have to close that and again open it so that the entire data will be loaded from first again. This consumes very huge amount of data, like easily some several hours, 1 or 2 hours per folder. And we are talking about each and every individual who is working on the engineering team. So they have to go through this much painful process to just download the data and try to find which is the right data for them. And one of the other problem is that They don't have any additional capabilities such as like comparing with the operator logs, or they don't know what results are being produced by the algorithms, such as like vehicle status, ROS topic values. They just download it. When somebody says okay, it is not working well, they will just download the ROSBAG file and try to simulate in their environment, and try to see if they matches with their opinion or not. But it was highly, what do you say, like inefficient system, inefficient workflow that was already present. So that is why there was a strong need of developing a data platform. And also, there are other reasons why we use this ROSBAG data, which are mainly for annotation, troubleshooting, and finding out the scenarios for and development, data passing for labeling, and also like auditing and storing purposes. So this entire process is was not there. Like most of them were done manually, and every operation takes like 30 minutes to 1 hour, 2 or 3 hour. Sometimes like data passing takes 3 to 4 hours per bag file. And it's there was a lot of people involved who works only with the data and try to clean up. So to give a perspective of metrics, so for 1 day's data collection, it usually takes 21 hours after the data collection to just find out the right data for them. And this doesn't consider any data sampling or parsing or any other process. So just to find out the backfill that they want, they spend like 21 hours for 1 day worth of data. Imagine doing this for 1 week of data or like 1 month of data. So it is just a painful process, and they usually spend 1 or 2 weeks just to get the right amount of data or right type of data to start their development. And there are also a lot of constraints, such as laptops. Our laptop doesn't have that much amount of data, so you cannot store the data in your laptop. So every time you download, you use it. If you don't want, you just make a note of which file you want and you delete it before downloading next. And it's manually we have to note down where is what file and whether the link is present or not. So it's all kind of uh, inefficient like workflow they were having earlier. So, based on all these problem statements, the first requirement this project came up, where we have to develop a robotic fleet data management tool. So we are talking about multiple vehicles, autonomous vehicles producing multiple data, each one of them doing their own missions. Each one of them is being tested for different sensor configurations, different algorithms. So what is the right way to combine these two, all these data, and channel in certain way that the final data pipeline produces the usable data, and also it should not create any kind of confusion to the end users who are our engineering teams. So mainly it has to use vehicle status data, ROSBAG data, operator log data. I will explain every one of them, each and every one of them in the upcoming slides. Not only like we have to store the data, they also had a need of visualizing them because Orbis was not good enough. So it will be good if all the data is stored in the cloud or somewhere outside their laptop, and but in a very secure manner and organized manner. And also if they can visualize them in cloud, and if they can download only the data that they want, that is what they were looking for. And out of say like 8 hours of data collected in a day, um, only half an hour data or like 1 hour data is really useful. So other data that we collected, they can be kept in some kind of a cold tier, where the frequently data is what everybody uses, and it usually be in terms of like 5 minutes, 5 minute back files or 10-minute back file, based on each and every scenario. Then there is also a need of linking all the datas. So when I say linking, we have to understand that the ROSBAC data is a sensor data, which is the input to the system. Vehicle status data is the ROS topic data, which is produced by our algorithms, and operator log data is like the final manual data that is entered by our testing personnel or the operators who wants to give us more information of what was going on during a mission. So these three datas has to be linked together so that we can understand for a given input what is the output that is being produced and what does an operator says for it. Earlier there was no such system, but there was a big need for us to develop this system so that um, the time taken for our engineers to build a algorithm or to test an algorithm, it should be fast enough. And some of the couple of things to consider is to add all the features which we were not having. That is to add a single sign-on for security reasons, data upload, querying in a multiple manner as per the user preference. Like each team have their own preferred way of searching the data, maintaining a data tier, and previewing the data, clipping, tagging, and linking it with Jira ticket and commit ID. So here, why we need to link with the commit ID is that um, our the data which we are collecting is from an interface ROS node. Again, it is built by our team. So they also have to validate like how good these systems are, like whether the interface nodes are performing well or no. So every time these codes go through changes and they want to know for a given commit ID, what is the data, and that's how they understand if the data quality is good or no based on whether like how successful that particular commit ID is. So before getting into the detail, I want to give an overview of the data platform. So the data platform which I'm talking about is a full stack data management platform. It has a user interface where everyone tries to like everyone can log in and based on their roles they get access to view certain data or view them, explore them, download them. So based on their roles they can also do some kind of an data operations like clipping, passing. So this is what like the that is the front end part, whereas the back end part is a process. It combines both a process and an elastic ELK server. So elastic server is a ELK server stands for like Elasticsearch, Logstash, and Kibana, and it is a open source tools which are used to for managing NoSQL data or like the data that we can get from the vehicles. So any data that needs real-time monitoring goes to the ELK server, and any ROSBAC data goes to um, the storage block of our in-house data center. The tech stacks that we were using are Foxglove and TypeScript for the front end, uh, Python, Postgres, Node.js for the backend, and also Elasticsearch, Logstash, Kibana, and Beats. Here, I want to give a special mention to Beats. That Beats are an agent that helps us to collect data from our vehicle. There are we used like three main type of beats: metric beat, file beat, and audit beat. I'll explain in detail how we used it. Now about the type of data, I want to give a small abbreviation here. So ROSBAC data, I mentioned as RBD. Vehicle status data are nothing but the ROS topic data and the logs which we get from the vehicle, and it is called as VSD. And operator log data is the manual entries that is created that is created by our testing personnel, that is called OLD. We also have a tool called Launcher, Visualizer, and Logger. It is an onboard application that is used by our operators to operate the autonomous vehicle. So once after booting the system, uh, they open this launcher, visualizer, and logger, and they launch the application. They can visualize all the sensor values, like if everything is good or no, and they can start logging, and that is when the actual logging of ROSBAC file takes place. And this tech stack was already built using the Python. So once the requirements were given, I started building the architecture. Now I'm considering four different zones here. The first zone is a autonomous robot zone, where this is where we produce data, and the main data uh, shipping agents or beats, and also I was talking about three type of data, in which the ROSBAC file is a very huge amount of data, and it cannot be sent to cloud in real time. So, and there is no such requirements like we need the data in the real time. So those data are uploaded manually, whereas the other data are collected, like other data are sent in real time to our AWS servers, where Elasticsearch, Logstash, and Kibana are installed. And the way it works is like it doesn't depend on anyone to launch. As soon as the vehicle computer is started, it can start collecting the data, and it helps us in a way, because we can understand right from the booting process, like what all logs being produced, and I will go through in detail, so that will help you to understand. But here I want to focus on in a very high level architecture, where autonomous robots, they have Beats agent that collects the data and send it to cloud, and in cloud we have ELK server which receives this data. uh, uh, so Logstash, what it does is it gets data from multiple sources, because we are dealing with multiple different type of files. So for each type of file sources, we have different input to output data pipelines, and it goes through different pipelines, and we extract very important information uh, using a grok filter pattern. It's equivalent to regular expression. Once those data is filtered and assigned as the key value pass in the JSON, they are ingested into the Elasticsearch. Uh, so once they ingest, they go to a specific index based on the time and the vehicle name, and some of the standards naming conventions that we use. Based on that, they get indexed and stored in a certain format in Elasticsearch. And we use Kibana to view these data. Not only view, but Kibana also helps us in user interface to configure Elasticsearch, create users, and manage them. We can also create multiple dashboards using Kibana. Now, the other type of data is like ROSBAC data. They are stored as a file format, and all the metadata are stored in Postgres. And operator data is also stored in the Postgres. Now, in zone two, in AWS or the cloud, we have all the data stored. But how do we use this data, and how do we achieve all the features that we were talking about before? In that, for that, I developed that data tool, the which is a front end part, and which is based on Foxcloud. It also uses ROS for some of the operations like data sampling and data clipping. But it's a Python plus Foxcloud based system. It has like multiple services running, and what it does is it pulls data from Elasticsearch, depending based on certain indexes, and also data from our file systems and Postgres server, and they combine into a format which is like very easy for our engineers to use. So that is the zone 3, which is application layer. The next one is fourth one, which is a workspace, where users can log into the system of our data tool by using Google SSO. So here I would like to explain the data flow in detail. So the first one is the zone 1 is the first zone, It's a fleet zone which is robot. Like there can be multiple robots sending trying to send data, and by nature of this, it is heavily protected and highly secure zone, and no request can be made from outside, and all data must be pushed, not pulled. So once the vehicles are started, they start pushing the data to the cloud environment, that is through an LTE connection. Then in zone 2 is where the data zone. In cloud, we store all the data in Elasticsearch, Logstash, and file system and Postgres. uh, the zone 3 is the application zone. So again, the data which is required for the application zone can be pulled only from the data zone. And the main two applications are Kibana and data platform. And we also build some APIs for other teams to use. So any data which is requested by uh, a user should go through the channel of application. Not only like human user, like any application they want, it has to go through the application zone. So by this way, we ensure that nobody has direct access to the database and nobody does any accidental change. And through our process, we manage the data properly, and we ensure that the data quality and the data uh, the data is maintained in a very safe manner. The last one is the data workspace zone. The workspace zone is where our team can view the data, like they get access to the data platform and they can view it. And it is subjected to user agreements. So the users are responsible for any type of data breach that can happen. So if they download the data, they are responsible for the data that they download. And this data is considered as one of the important asset for this technical team, and also for as a autonomous vehicle in industry who's working on an airport application. There is no such data available in openly available in the outside world. So this is a very huge asset, and managing the data and security, managing the securities of the data is a very crucial process in this regard. Here the arrow mark indicates the data workflow, only allowed data workflow, like how the data travels from one place to another. And also I have also given a shield, the complete black shield means it is fully protected, whereas off open is where some channels are open between one or two zones, whereas the complete white is where the possibility of data loss can happen, like something like somebody can download and send it to somebody else. But it is again, every we consider like every employee is should be sensitive enough to have the data and not share it to others. So as part of this data platform features, we developed 10 main features. I want to go through in detail. So data collection first. So data collection, in this part of data collection, as for all these three type of data, we go through individual process of like how efficiently we can collect the data and continuously send, because we are here dealing with some very huge volume of data. And not only volume, and it is also high velocity of data, because this is produced, some of the data are produced in a 10 hertz, some are in 1 hertz. So these data are continuously sent to the cloud. And there should be a careful we should be also careful that these data collection nodes should not affect any of the existing algorithms in production, because this can it should not take, it should be as light as possible. That is the main concern. um, Data storage, it is about how efficiently we are storing. We have two tiers, like hot tier and cold tier. And hot tier is where we have a very important data which are frequently used, and cold tier is stored for the later purpose, and it is low in that nature. Data search is if somebody wants to search, there should be a search way of searching where they can give us any keywords or any string that has to be searched in the database, and they should get the data. So that is the data search. Visualization is where they can view all the camera and the lidar datas. I will show in detail in the coming slides. And the provision to data download, update the data, linking the three type of data as per the time frame. Data passing. I think I explained it earlier, but the data passing is when they take a certain ROS bag and extract all the image frames from it, and from these images there should be some images sampled from these complete frames, and those samples are sent for the annotation. So it's somewhat a rigorous process that we have to go through to perform annotation and the labeling. Snapshot is an important feature which helps anyone to mainly check, say there is a certain scenario that happened. What happens is if I see a data which is very interesting, and say there is a class label or there is a frame in which the algorithm didn't work properly, I want that particular frame and annotate and use it for my training. I should be able to quickly click on one button and just download that frame. Earlier this functionality was not there, but as we are viewing all the data in one place, we are added that feature to download the frame instantly. Data clipping is nothing but if you consider this data as a video, like if you want an subset of this data, for 5 minutes, like you want only 1 or 2 minutes of the data, then we can do the data clipping by selecting the time range. So ROSBAG data, as part of the ROSBAG data, it is collected by level, and it stores on the on-premise data storage. It consists of all the sensor data like camera frames, RBG camera frames, thermal camera frames, lidar raw packets, localization topics, and the sensor topics. Vehicle status consists of all the data that needs real-time monitoring, including CPU utilization, memory utilization, any system-related logs, interface-related logs, or any stack like AI related like perception, planning, any ROS topics that needs monitoring. They are collected. They are considered as a vehicle status data, and they are collected. Operator log data, like I mentioned, it is a manual log by our operators. For UI design, we went with the Foxglow mainly because it is a web-based portal, and so it is a web-based visualization, and it is easy for us to manage it in cloud so that anybody can like log into the system from their laptop and they can use it. And it's a more mature product and open source. So we decided to add extension to this Foxglow open source project and use it for our purposes. So for data collection, this is the list of metrics that we collect. The main ones are CPU utilization, GPU utilization, disk, and a system. These data are collected using a metric bit. So if you want to know how much performance, like what performance every node has, we can monitor the processes list and check how much CPU utilization and the memory utilization it has. So any kind of inconsistencies that happens in the algorithm, it gets directly reflected here. For example, in our case, we had some problems in interface and perception stack, mainly because of some unknown print statement or something like some of the algorithm shortcomings, like it wasn't efficient enough. So these kind of things were well evident. We can monitor them, and it also helps us to have a threshold like design parameters. For example, for perception, we can say we should dedicate only like 30% of the maximum we can take is 30% of the entire CPU space. then what happens is like our engineers try to curate the algorithm in such a way that we the algorithm's utilization lies within the safe levels which is dictated. Other monitorings which are done are system interfaces. So in system interfaces, it is more on like a hardware software level. Mainly the camera packet drops. So any hardware parts such as like wires or interfaces, they may subject to wear and tear. It may affect some of the packet drops, or like even the quality of the wires that we choose might affect the data that we collect. So those things are monitored by using metric bit. Again, they monitor all the interfaces and check for packet drops. And I also used some of the bash scripts to monitor USB, Ethernet, and PCI interfaces health. It gives like how much bandwidth it is having and how much is being used. Um, some of the data are not used always, so we use cron job in the vehicle computer to log them continuously in the system files, like every 1 hour or every half an hour, depending on uh, the frequency in which it may change. And once they are written to the system files, the FileBeat agent looks into, I mean, they monitor this file for changes, and every each and every line is again captured and sent it to the Logstash, I mean the Elasticsearch part. So I also want to yeah, so other log messages like ROS master log, launch nodes, node performance data. So these are the some of the important metrics that we collect on a regular basis. It helps in both the ways. One is later, like if you want to troubleshoot a certain issue which is unknown, which is not captured through other methods, these logs give a very detailed picture of what is happening. For example, these logs have what all nodes are active at this moment, and what all nodes are publishing what topics, and what are the nodes which is subscribing to a certain topics. So all these data are already like available in this log messages. So storing them will help us to troubleshoot in the if any issue happens in the future. Having these logs as part of our testing, it helps us to understand like, okay, this is a pattern our platform is following. ROS topic collection, again, it is in our case, we used vehicle status, velocity, wheel angle, brake, steering, throttle. So these are some of the important ROS topics used for analyzing algorithm performance. In next slide, I have very detailed list of all the important metrics that I suggested and included in the particular data collection process. And also support for the robotic fleet management system. It is APIs that we develop so that those fleet management systems, before planning, they get the data from our system. So here, one thing to notice, like there is if there is a vehicle A, they need a data. If they need a data of vehicle B or vehicle C for their decision process, because they have to coordinate and work, then they get the data from our data platform only. And this is like so there are some APIs that I developed which they use and try to poll and get the vehicle statuses. So performance metrics, there are two categories. One is general and the team specific. In general, CPU temperature, GPU temperature, LiDAR temperature. So these all these temperature values helps us to understand for a given environment whether the vehicle is performing well, and if there is any like deviation in the performance or no. So for autonomous vehicles which is operating it outside, it operates in a heavy sun or like a heavy cold environment, rainy. So all these conditions might change the physical metrics such as the temperatures, and uh, it is very crucial for us to monitor them, because sometimes the overheating of the computers also can cause restarting of the system, and it can lead to a catastrophic failure or the vehicle crashes. Here we also monitor battery I mean battery charge, like how much battery is remaining um, in the system. And again we also collect vehicle states, autonomous vehicle performances. um, so for planning, perception planning, mechatronics and controls, we collect computation time of each and every modules. For perception, we collect bounding box results to to understand if the vehicle, if this is for the testing purposes. Again, so planning, in planning, we collect all the mission related, like how much AD here stands for autonomous driving. So autonomous driving versus manual time, and for each mission, how much autonomous driving is done in terms of time and distance. Where is the current destination area, and all these data are time series data. They are collected continuously. So for every time frame of input data, we have corresponding output data. And what is the, like, with this we can understand like how, what is the latency of the data from one module to another, and what is the efficiency of the algorithms, how it is affecting other modules. So all these insights can be derived from the data that we collected here. So next, I want to show the Explorer. There are like 4 slides ahead, which shows the UI. So Explorer here is something which is similar to the file Explorer we use on a daily basis in our operating systems, like either Windows or Linux. It is arranged in a folder structure by date, and once you enter that folder, then again you will be having subfolders with the data in it. There is another view called a list view, and in list view we can see all the details of the folders, such as folder name, in which location it is, which location we collected this vehicle name, and the size of the data. And we also have the view and download buttons there. So when you click on view here, it directly takes you to the visualization page. It also has other metadatas, like information and the events. The comment section is something which is which you can add. All these fields are editable. This is where the manual edit comes into picture. Now, one more thing to note down here is all these files and the metadata information are, they are from 2 different data sources. They are combined here and showed in a single window. So for the user who uses this system, they will have all the information that they are looking for at one place. Whereas for others, like, whereas in earlier time, they were not having such system. You can also see that the info, along with the information, there is also event list. So this is an high level event list which is produced by, it's equivalent to operator log. So it comes with a time frame. So in next here in visualization, I would like to show you like how it looks like. So you can see in top there are 3 tabs: ROSBAC data, vehicle status, and operation log. So these 3 type of data, one common thing between all these is the time frame and the vehicle name and the area. Once you have that particular combination of data, you can jump between this data and identify which is what. The first one is ROSBAC data. Here I'm showing the 5 cameras and the LiDAR data. And in bottom of the page, you can see a slider, like something like an video play button. And this video play button is for playing this data. And this Foxglove, you can also see the Foxglove, what do you say, like Foxglove demo site for this something similar. So one of the important features that we have is we can jump between the time frames, something like how we usually do in YouTube videos. And unlike Orbis where we cannot jump, we can jump between two or three. And if you want to play a certain or rewind again, you can go back to a certain time frame and then play again. So this is what so this is one of the main features. How it is helping is, so you can see the mission start, a purple color line, a vertical line along the play. Uh, so this vertical line is nothing but the events that are produced by the operator log. So here we can see that data linking happens, and for the given time frame, if someone is typing something during the vehicle operation, that those data are shown here. Now, the next thing to note here is, um, once we see the mission start, once we see the mission start to mission end, like we can just drag the data and clip only that particular data. So in the bottom part, there is a create clip back file. So, and there is a slider given, and that slider denotes the start range and the ending range. Once we give that ending range, once we give that start to end and click on clip back file, it can clip the data for that particular time range. And it is a backend process that it creates, and it doesn't stop you from exploring further. You will also get a notification at the end once the that clipping is done. Again, there are some tools which you can see on the tools bar, like which is in the bottom right side. There is a camera icon and the clipping icon. Those things helps you to like snapshot the video, or take a snapshot where all the frames are downloaded as an image and a PCD file. And there is also another provision to tag the datas. So once you jump to the vehicle status data, it will show the data which is corresponding to that particular time frame and the vehicle computer. And here you can see all the data in terms of both plots or strings or tables, like whichever the format you want to see. And I want to here mention some of the use cases. One is say there is a control engineer who is testing, and while he's testing, he's checking that actuator is getting a certain value and it's an anomaly, and he wants to know what is the perception value looks like. So based on that data, there is a cursor which like there is a vertical white color line that you can see. That is a cursor line which directly gives like what is the corresponding value in the other thing. Not only that, you can also compare exactly with the what input frame. So what our sensors are seeing, what is each and every modules are giving the results, and what is my module giving the results. So this is like a perfect tool for testing purposes. And the next one is next use case can be the labeling. For labeling, if you have an operator log who says like, okay, this is a very important part, they can just jump there, and they can clip that particular data and use it for further like parsing and labeling. I want to give a very quick go through the data security. For data security, we use user management. We use Google SSO. Let me jump to the main part, which is user role mapping and the role feature mapping. So the first thing done, 1 minute. So the first thing I did is to list all the features, like Explorer raw, Explorer clip, Explorer snapshots, like that. Like I listed all the features. Now, the access was given based on roles and users. So for every role that we define, there can be multiple features access they have, and every user can have multiple roles. So this helps us to assign multiple roles to the user, something like a developer and tester, or the tester and operator. And based on their roles, they have a specific access to features. And here we can also mention that I have mentioned For example, in the last one, VSD, visualization download date area, download vehicle. What that means is, say there is you get a contractor who has access to only one vehicle type or one area. Then you restrict all the data to him for only that particular area. So, and how it helps is like they cannot view other datas, and it ensures that you make sure that only specific people get specific access to the data. So this is a slide which we already saw. This before implementation, what was the general workflow used to by all the teams. After implementation, what happens here? Now, after implementation, the data collection is same, but after the bag file is collected, we have an explore, and in explore, to explore the file, it takes less than a minute, because there is a search bar which is available, and you can also, it is organized properly, so you can search by date, vehicle name, or the area. Once you find the folder, then you play the data, and it's not like it is not mandatory for you to play the data from beginning. You can jump to the data based on the comments already given by operators, or based on your own experience, like you can just jump and quickly check or quick look into the data. This saves a huge amount of time, and even if you realize, okay, this data is not present, it doesn't take much time to click into next backfile and check that. So as per our estimation, it takes like 1.8 hours to check 1 day worth of data, which is like uh, fantastic, because in earlier times, like what happens is it took about 21 hours, where here it takes only 1.8 hours. It is just to get to the data that they want. Again, on top of that, they can perform data snapshot, clipping, data passing. I have also mentioned how much time it took for us and how much time it saved for each and every feature here. Here, I want to give a special mention to annotation and the labeling workflow. For the labeling, annotation and the labeling workflow, again, after data visualization, there is a provision to pass the back file. So there are some details I didn't mention. Like one is what are the deep learning projects that we have. So based on each and every deep learning projects, the type of data and the sampling frequencies changes. Those are already configurable ones, and they have buttons to just start the passing. Um, and it usually takes like about 10 seconds per frame, and 10 minutes of passing per back. And as it is like quick, as it is all backend processes, because we don't have to view like how it is being passed, they happens in parallel, and they happen in a backend. So our engineers, like they can focus more on the viewing the right type of data and selecting them and sending it to the backend process, whereas the system takes care of the sampling them. Now, once they get the passed data, which consists of all the frames that they want to annotate, they are separated based on what purposes. It can be something like 2D object detection, or 3D object detection, or line detection, or any of the or like some kind of segmentation they want to do. So based on what use cases they are looking for, those data are collected and grouped them and placed in certain folders. And as per our estimation, this takes like 3.5 hours for 1 day worth of data. And this is like a very huge like huge time saving. It usually takes like 2 to 3 weeks of sampling and sampling work alone. And it is done by two people, whereas here only one person can handle, and they can dedicate only half of their day's work for the sampling process. um, our in our company, this once the data is created, this there is it is placed in a shareable location, where the location is shared to the annotation team, and they take care of the annotation part. So at last, like, I want to mention some of the performance improvements. So, like, what are the challenges that or problems we faced, and the solutions or the learnings that we got from it? So, there are some design parameters, something like the data frequencies and the number of topics that we collect and the time. So, based on these three type of data, the data volume increased drastically, and in Elasticsearch, you cannot place like some 100 GPs of data in a single index. That will affect the performance so much. Not only for that particular index, for any indexes, like it won't allow you to. The system will be very slow and it will fail, saying that response time is over. So the here the important thing that I learned is how to index those data properly, how to, like, what is the volume in which they can handle. And I realized that it can handle like 1 GB of data maximum, or like based on, again, it's all based on the computers server configuration that you use. For our purposes, we chose 1 hertz data for specific topics, and for some very critical ones we chose 10 hertz. And when it comes to index, we like those indexes are created for per day per vehicle basis. So this helped to improve the performance of Elasticsearch and the searchability of the data by a huge amount. One more thing is, we also had a constraint um, in loading or like visualizing the data in graphs, mainly for the big data that we develop. Earlier, we used very conventional Bootstrap, Vanilla JS, Postgres server, that part, but it didn't work properly because we had to work through so many algorithms, and we didn't have like enough time to develop everything from scratch. But one of the important design decision that I made is to go with React.js and the TypeScript, which is very easy to manage, and also the Foxglove platform that we chose was working very well. So it helped. By making these important decisions, like, we are able to improve the performance of the entire platform. So next, I want to explain about my deep learning experiences at ThoreDrive. So here, mainly I worked on deep learning side. I worked on three projects. One is LiDAR segmentation. So before joining the data team, I was working in a perception team, and here in the LiDAR segmentation, so the earlier they were using DB scan. So for LiDAR segmentation, as you might know, the LiDAR sensor produces LiDAR raw packets, and they are again converted to a point cloud by combining or like integrating all the raw packets. Um, then these point clouds are clustered, and each cluster is considered as one object. And these clusters are based on the EPS values that we select. So here EPS is nothing but the distance between 2 points. Uh, so by selecting a certain EPS, we can either shorten the volume of cluster, or like we can make it enlarged. But one of the difficulty we face is it is a airport domain, and it consists of very small objects to very large objects like airplanes. So it is not easy for us to come up with a constant EPS value and then expect the clustering to work for both small and large objects. But somehow, like, they were handling earlier with a certain error. Then also computation time of the DB scan is very high because of the complexity of the algorithm itself. Like, it has to go through each and every it has to go through each and every points and check and to make a. I mean, basically the complexity of the DB scan is very high. Again, due to the constant EP value, there was often a problem of over segmentation and the under segmentation. Over segmentation happens for say like cluster of some group of cones placed together, and say there is a wing and there is a person stands near the wing. They all grouped as one particular the wing and the person is grouped into one cluster. So these kind of problems were happening. Those were all like handled heuristically earlier, but then we decided to scrap this and go with the 3D object detection, which is a deep learning model that we built based on center based model. This in this particular paper, they defined one particular 3D detection object detection module of using lidar data, and they used encoders like voxelnet and the point pillars. What it does is first it tries to detect the center of the object using a key point detector, and try to regress it to other attributes such as 3D size, 3D size, orientation, and the velocity. So in this case, what I was working on is to augment these point pillars with spectral similarity matrix. So spectral similarity matrix is the same matrix which is used uh, in the spectral clustering, where this similarity index gives uh, it gives a high value if the data if two data are lies on the same direction, like it considers the eigenvalues and eigenvectors into picture, and it considers the data as a same cluster if the data is in the same, if the arrangement of the data in the same direction. And this deep learning model on overall it provides like a 50 to 60% speed gain, and the metric used to for accuracy is like mean intersection over union. I mean, it's not accuracy, but we used mean intersection over union as one of the important parameters to train them. um, I was not completely working on the project due to the budget issues, and also the fact that I moved to the data team. But I really worked on the augmentation part and developing the deep learning part of it. So the next project I also worked on is a 2D object detection. Here for 2D object detection, they were using YOLO V4, but later were upgraded to CenterNet. And in this case, we realized that CenterNet is the most accurate model and can achieve better performance. So I was working on some addition of more classes to the system, and I helped them for training. Um, this CenterNet proved to be was proven to improve the detection accuracy and intersection over union. So the next part is the I want to discuss about one of the algorithms that I was working on. Again, this is based on the paper called fast segmentation of the 3D point clouds. So here the problem is the problem statement is we have the point cloud, lidar point cloud. For each point, we have to label whether the point is a ground point or non-ground point. Because before sending the data to clustering algorithm, you have to remove all the ground points, because those can cause a very huge problem. And here in this case, some of the requirements is that it should have high computational speed, um, low complexity, and less development time. We were looking for developing something within a week time. So anything which is very intuitive and which can be easily tested, that is what we were looking for, and we came up with a particular algorithm. So this algorithm goes in a way like first uh, there's a iterator involved, and for every iteration I select lowest high value points, like the points which is along the ground level, and here we are seeding points. We take only small seeds, like some samples from the lowest high value points, After taking them, using those points, we try to estimate an initial plane model. And this initial plane model is based on the plane model equation which is given here. We perform SVD on this plane, on this data which we collect. The SVD gives eigenvalues and eigenvectors, and the eigenvector corresponds to the smallest eigenvalue, provides the least variance distance, and the plane and that plane is estimated with the least variance direction. So after having this plane estimate, we check with every point its orthogonal projection and on this candidate plane, and see if like how close they are to the plane. If they are very close, they are considered as the ground points. If they are very far, then we consider that as non-ground points. And we repeat this process to a point where there is a conversion happens, and we also saw that it converges very fast and able to identify ground points and non-ground points with a very good accuracy. Um, so the next one I want to discuss is about estimation and tracking algorithm that I was working on. So for estimation and tracking, there was already an tracking algorithm that they were using. Here I want to mention two main problems that I helped them solving. One is the issue of missing track ID. So how do we measure this issue of missing track ID is between the detection to the tracking ratio. So from the perception module, like from deep learning module, we know how many objects are being produced, and then we check how much on a given frame, like how much objects are being tracked. And we realized that many of those objects are not tracked properly. That is one of the main reason is the issue with the DB scan lidar segmentation, as it was clustering the I mean the over segmentation and the under segment was happening frequently. Um each of the cluster was breaking and moving a lot, because of which like it didn't follow any of the principles of like constant velocity model or any of the Kalman filter models, dynamic models. So because of this, what happened was it was not able to associate with the previous values, and it was able like it was failing. Um, there was another problem that I saw, which is uh, velocity estimation accuracy. So for static objects, it is expected that the velocity of that object should be zero. Whereas in when I was working, I saw that like a lot of object static object had a velocity component, because of which there was a lot of jerk in the vehicle. So whenever it sees either a cone or something like a physical structure which doesn't move usually, uh, when it has a velocity profile, the vehicle thinks that there is someone moving, and it considered it as a risk and try to stop. In next immediate frame, as it is having the velocity zero, it considers as it has stopped and it tries to move. So it's kind of a jerk that it experienced, and it affected the user experience. So how I dealt with this problem is by going through all the algorithms again, mainly the external Kalman filter. I fused lidar object detection and the camera object detection, and it helped to improve by a certain level. But the main results were achieved when I was prolonging the tracking of past objects. So I before uh, so if any object is not identified for next two or three frames, it is usually removed from the tracking. Whereas in this case, I try to predict their location and keep it for quite a while. And this kind of as I improved both the dynamic model and also try to like prolong the prediction, it was able to estimate the velocities more accurately than before. So the metrics that I used to measure all these are static object velocity for the static objects, uh, deductions to tracking ratio, velocity, and the direction error of the dynamic objects. These are the metrics that I mainly used and tried to improvise. At last, I want to go mention one of the machine learning project that I worked on. This was with Intelligent Maintenance Systems Lab in collaboration with Mazak. So Mazak is a CNC manufacturing company. As part of this company, their requirement is to predict when their CNC machine is going to fail. They had some of the frequently occurring patterns. Usually, when there is a low lubrication or tool imbalance or the broken spindle. So they needed a system which can predict the failure even before it happens, or like it when it shows a very like machine level signal changes. So in order to address this problem, what we did is we used a vibration and the current sensor time series data. These data are collected for new machines and also the old machines with the low lubrication, tool imbalance, and the broken spindle issues. After collecting the data, they are classified as healthy and non-healthy machines. As it is a time series data, we performed a fast Fourier transform on this time series data, along with the other statistical features that are usually used for the time series data. And once these features are extracted, we select the data features by using a Fisher score. This helped to reduce the feature list from 20 to 25 features to 10. Then again, we performed a principal component analysis and selected the reduced dimensions. This again reduced the dimensions by 2 to 3. Actually, three dimensions. Then later, with the reduced data, we performed multiple machine learning models like logistic regression, support vector machine, self-organizing maps, and decision trees. Our goal was to check which of these machine learning algorithms are performing well for this particular type of data. And we realized that the logistic regression gave a maximum accuracy for the given data set. And one of the main like helpful thing about logistic regression is, in spite of giving absolute zero or absolute one as the result, it gives a probability of probability. It gives in terms of probability. So the one is considered as absolute healthy, but as the vehicle is going on through wear and tear or some kind of lubrication issue or due to the operation, we monitor, like we saw that it slowly moved from 1 to 0, and based on that particular observation, what we did is we made a section. So 0 to zero point 0.3 or zero point 0.4 is considered as a critical condition, and 0.4 to 0.7 is considered as a maintenance required condition, and 0.8 to 1 is considered as a healthy condition. So whenever it goes to the range of 0.4 to 0.7, a maintenance request is made, and they try to fix whatever the issues are found in the CNC machine. So by this way, they saved a huge amount of time, not time, mainly like maintenance cost, and they were able to predict even before the spindle was failed. This also saved a huge amount of time in terms of parts. Any These machines cost somewhere around 1 million to 10 million US dollars, and each of these parts can cost around like 100K to 500K depending on how much big the machine is. So this was very helpful, and I also got a chance to demonstrate this in an international manufacturing forum on behalf of Mazak. I was presenting it mainly directly to the clients of Mazak, and I got a very good appreciation on this. Um, So there is also a full stack development involved, which in which I developed it using a Flask, HTML, CSS, Vanilla, and it is mainly used to monitor the health values in a real time. So yeah, we are at the end of the presentation. I believe I have explained all my works in a detailed way and in a clear fashion. Um, yeah, I'm open for any questions that you may have during the next interview processes. And yeah, I'm very excited about this interview, and I'm looking forward to it. Thank you.